Hello everyone, again welcome to this NPTEL course on Advanced Species Concrete Design. We are in this fourth week, part 4 of the module. In this lecture, we are going to focus on ultimate moment capacity. So, how to derive the ultimate moment resistance. In the last lecture, we derived the entire moment curvature response of different sections, and in this video, we are going to focus on how to calculate ultimate moment capacity, particularly focusing on IS code provisions, IS code and then IRC code provisions. Okay, the expected learning outcomes, the student should be able to determine the ultimate strength using strain compatibility method, and we will also explain what are the approximate code provisions for calculating the ultimate moment. Then finally, we will talk about how to use this for analyzing a flanged section using both strain compatibility method as well as using approximate method. Right. So, if you take this cross section like the one that you see here, so if you take just the cross section, I have just put a elevation of a longitudinal elevation of a member, but actually we are doing a section analysis. So, the section, let us say that it is rectangular. So, if I say perpendicular to this plane, I am going to have a width of B. For this section, if you look at it at ultimate, we are saying that ultimate condition corresponds to the concrete reaching a strain, usually for bending it is 0.0035 as per IS code provision, right. Now, if your strain at failure, okay, if it is going to be greater than your at ultimate, if it is going to be greater than your epsilon p u for a balanced section, typically for balanced section we will take that as an yield condition. So, yield condition, then we say that that is going to be basically an under reinforced section, right. So, this is your initial strain, and this is your final strain, and this is nothing but your delta epsilon p, that what we have talked about, right. So, for a balanced condition, delta epsilon p plus epsilon pi will be equal to yielding strain. So, that means what we are saying is for an under reinforced condition, the strain at ultimate will be greater than what you get for a balanced condition, or in other words, it is going to be greater than the yielding strain, right. So, this is the strain in the steel for the balanced section, and typically epsilon pu balance we will define that equal to epsilon py, some yielding, right. For a balanced condition, we know that both of them will reach simultaneously their limits. That means epsilon cu will reach 0.0035, and this epsilon pu, the total strain will be equal to some yielding strain, that what we define, right. So, that is your balanced condition. In case of a over reinforced section, epsilon cu will reach 0.0035, that means it will fail in concrete compression, but the steel would not have reached yield, or epsilon pu will be less than epsilon py. Now, what is the yield strain that we have defined in the previous material models, depending upon what kind of constitutive model that you are using. We have seen simple elastic perfectly plastic, or simple elastic hardening, bilinear curve, and depending upon that you choose your yielding strain value. But in general, in balanced condition, it is a hypothetical, or I should say is a special condition where both concrete reaches its failure strain, steel also reaches its yielding strain. Now, because pre-stressing steel does not have a well defined yield plateau, we define yield some either you take 0.2% proof stress, or the code gives you what should be the yield strain that we need to consider. Okay, so this is the stress strain curve model that we talked about. If you see here, if you take this as your representative curve like this can be idealized like what is shown in this figure. Let us say the black color curve, that what we say. So, this you take like this straight and then you put like this. So, this is a idealized bilinear curve, right. Now, we can also idealize this with a factor of safety in a very simple form like what it is shown here. So, you go here all the way and you knock it down and then you go here. So, we have explained in the material chapter how do we get these values using IRC code provisions. For example, if you look at the idealized bilinear curve, my yield stress is 1408 megapascal and the corresponding yield strain, this will be your epsilon py, which is 0.0072, and your ultimate is going to be 1588 megapascal and this is your epsilon pu, okay, ultimate. So, this is the ultimate conditions as per this idealized bilinear curve, which is what this is what we are going to use. This will be used in our calculations, the idealized calculations, idealized bilinear curve, design curve. So, why do we say that as a design curve? Because we are applying partial safety factor for material, that is for steel. So, we knock it down by 1.15 and then you get this curve, right. So, now we have understood what are the different failure modes, which is an under reinforced failure mode, balanced mode and over reinforced mode. So, under reinforced failure mode will happen when you put less steel, and over reinforced will happen when you put more amount of pre-stressing steel, and that will ensure that the concrete is going to fail before the steel is actually going to yield, just like what we have done in advanced reinforced concrete. Here also it is same. Depending upon the amount of pre-stressing steel that you provide, you can have all the three types of failure. You can have an under reinforced failure when you put less steel than the balanced, and balanced failure, both of them will reach same failure simultaneously, and in over reinforced the steel will not actually yield, right. Now, let us look at what is the strain difference in pre-tensioning and post-tensioning. Now, the strain difference, which is the initial strain epsilon pi, the strain in pre-stressed tendons when the adjacent concrete has zero strain. So, what does that mean? That means the strain difference gets locked during the transfer of pre-stress, right. So, what is that? If you look at pre-tension members, the strain difference gets locked when the tendons are cut. When you cut the tendon, because they are directly bonded with the concrete, when the tendons are cut, the concrete also deforms, steel also deforms, right. So, that strain difference is the epsilon c, the strain in concrete is 0 while you transfer the pre-stress, that means while you transfer the, when you cut the strand, right. So, the epsilon pi will become what is the strain in tendon just before transfer. So, epsilon pi is nothing but epsilon p naught minus epsilon c 0. However, in case of post-tension members, the strain difference gets locked when the tendons are actually anchored. This is when the strain difference is actually gets locked. The strain difference at that instant could be epsilon pi, which is epsilon p naught minus epsilon c naught. So, that means there is going to be a small compressive strain in the concrete at the time of bonding. That is what we explained in post-tension system. When you do stressing, and when the tendons are anchored, at that time they are not bonded with the concrete. So, when you at the time of grouting in a bonded system, then only both of them are coming into contact, right. There may be a small strain when you do the grouting process, because at that time some loading would have already happened, right. So, the member may be subjected to sulfate or maybe some nominal amount of superimposed loads, right. So, because of that, there may be an epsilon c naught that has to be included in case of a post-tension member. Now, how do we look at ultimate condition using IS 1343, right. So, again we take a simple rectangular section with the steel of area of pre-stressing steel AP, and you know that this is the ultimate condition. The strain is reaching 0.0035. At that point, we do not know what this strain, this we do not know, but what we know is epsilon pi, the initial strain, this one we know, right, but we do not know what is this delta epsilon p, right. For that, to calculate that, now we have to assume different values of XU like what you have seen here. And then now, so how do we, for this strain, how do we get this stress block? So, if you remember, for IS code, right, if you see the IS code stress block is like this. So, FC and epsilon C. So, this goes straight and then it remains constant, right. So, this happens at 0.002 and this is considered till 0.035. Now, what is this value? This value is 0.447 FCK. So, this is the design curve in compression, right. So, that is what we are using. So, all we have done is we have rotated this curve by 90 degree and we are plotting here, right. Somewhere here, if you see this is 0.002, it, this becomes, and this remains constant, I should say. Okay. So, 0.447 FCK, right. So, when you integrate all the stress block and multiply with the width of the cross section, then you get your compression force, which is Cu. And the stress block parameters for ultimate condition is already defined by the IS code. They are saying that the location of the Cu is going to be at a distance of 0.42 XU, right. And the value of this Cu is also given as 0.36 FCK B into XU. So, these parameters are already given just like your Whitney stress block parameters. So, here also they have given this parameters for Cu and Tu. So, now what is the Tu? So, we know that the equilibrium condition has to be satisfied. So, equations of equilibrium has to be satisfied. So, the net, there is no external axial load. So, compression force should be equal to the tension force. Now, compression we have defined as per IS 1343 like this, which is 0.36 FCK B into XU. Now, what is the tension force? Tension force, we know the strain in the concrete we are going to calculate based on the assumed value of XU as epsilon PU. Once epsilon PU is known, then the stress FPU is actually a function of your epsilon PU based on the design stress strain curve, that idealized design bilinear design stress strain curve, that what we have discussed in the previous slide. So, using that constitutive equation, now we can calculate your stress in the pre-stressing steel for a given value of your epsilon PU, right. So, for the assumed value of once XU is assumed and the top compressive fiber strain is assumed using similar triangle, now we can calculate delta epsilon P. Then we can also calculate epsilon PU as epsilon PI plus delta epsilon P. So, this can be calculated, but we should choose the value of XU so that the equilibrium condition is satisfied. So, that is the reason the XU has to be iterated to find which value of XU that satisfies equilibrium condition, right. So, once the equilibrium condition is satisfied, now I can take the moment. So, usually you can take moment about, for pure bending you can take moment about any point. So, we take moment about compression force location. So, the lever arm is going to be this, which is going to be D minus 0.42 XU. So, that is the reason the moment resistance of the section is tension force in the steel multiplied by this lever arm, which is basically yeah. So, this is the right. So, this is going to be your lever arm. So, from here we can get my moment resistance as tension force multiplied by the lever arm, right. So, this is the procedure that is given in IS 1343. The only difference what we are doing here is we are using the design stress strain curves for concrete and for steel we are using this idealized bilinear curve, we are going to use that, right. So, let us look at now in detail how do we get. So, how the equations of compatibility is coming. So, again from strain distribution, that linear strain distribution. So, we can calculate. So, this is nothing but your delta epsilon p. So, the delta epsilon p is nothing but epsilon pu minus epsilon pi, right. And let us see now how the constitutive equations are coming. For concrete, again as explained in the previous slide. So, we are going to use design stress strain curve for concrete, and the compression force, already the integration has been already done, unlike what we did using Whitney stress block parameters, because we are doing calculations only for epsilon cu equal to 0.0035. So, that is the condition. For that, if you integrate, the entire compression force is going to be 0.36 FCK into B into XU. So, this should be B, right. And for pre-stressing steel, because we are going to use bilinear curve, design bilinear curve. So, the stress in the pre-stressing steel should be function of your epsilon pu, because we do not know where the strain this epsilon pu is going to be. If you put, so this is your, we have taken Fp and epsilon p. So, we take this kind of a bilinear curve, right. So, depending upon whether my strain is going to be either here or here, I have to follow this bilinear constitutive equation for pre-stressing steel. So, that is why the stress is going to be function of your epsilon pu. And again this we have sent, we have assumed that bilinear curve, we discussed it in the previous slide. Okay. So, in an analysis problem, typically the sectional dimensions are given to you. So, that means we are given breadth, we are given depth, and we are also given with area of pre-stressing steel, and we also how much initial pre-stressing that we are given, epsilon pi is given. I have told you, typically we take epsilon pi as Fpi by Ep, and Fpi is going to be 0.75 times Fpu, right. So, we know what is the strain that what we are going to put, and characteristic strength of concrete is given to you, and also characteristic strength of pre-stressing steel is given to you. So, this is an analysis problem. So, entire all the dimensions are given, reinforcement is given. So, we are going to calculate what is the ultimate resistance and curvature at failure. Okay. So, the unknown quantities, we have to satisfy equilibrium, find out the neutral axis depth, and whole idea is to calculate your moment resistance at ultimate, and we do not know epsilon pu because the XU is not known. XU we are going to find out using equilibrium condition. So, these are the unknown quantities. Okay. So, the overall objective is to find ultimate moment resistance. Okay. So, this is what the section. So, let us look at now what are the steps that are going to be involved. Again, at ultimate, concrete in compression is taken as 0.0035, as per Indian codes we take 0.0035. So, if you look at ACE code, they take 0.003, but they are nearly very close to each other, right. Again, we do not know what is the XU. So, we have to find that XU. So, once XU is fixed, you are basically fixing this strain distribution, right. Then using similar triangle, I will be able to get my delta epsilon p, and I know epsilon pi, and epsilon p will be summation of your epsilon pi plus delta epsilon p. So, to do that we have to start with something. So, we assume a value for XU as a first instance. So, once XU is fixed, then I can calculate my delta epsilon p and I can calculate my epsilon p. Then Fp we know from design stress strain curve or pre-stressing steel, right. So, whichever the range that you are there, using that constant equation you are going to get the stress. Now, once the stress is found out, then we can calculate the concrete contribution in compression and steel contribution in tension. Now, we need to make sure that for the assumed, we have to make sure that C is equal to T. If it is not, then we have to either decrease the XU or increase the XU, right. So, this is what we are going to check. So, this is for force equilibrium condition, because you can never violate equilibrium. So, we have to ensure that at the section equilibrium is satisfied. Then once if it is done, then you can go ahead and calculate moment resistance M and the curvature. Again, curvature is very straightforward. It is epsilon Cu divided by Xu. Right. Now, in case if the compression force is going to be higher, if C is going to be higher than T, then we have to reduce Xu, right? And yeah, if C is going to be higher than tension, sorry, if C is going to be more, then yeah, it is going to be, you have to reduce the Xu, then otherwise you have to increase the Xu, right. So, either increase or decrease depending upon whether you are getting higher compression force in concrete or higher tension force in steel, right. So, in the strain compatibility method, thus the difficult step first is to calculate the Xu and FPU. To start with, we do not know at ultimate condition what value of neutral axis will satisfy the equilibrium condition, right. So, IS 1343 method allows to directly calculate these variables in an approximate form using table level. So, again this is valid for when you have very low reinforcements, okay. That means the table tacitly assumes that the sections are going to be under reinforced or heavily under reinforced, I should say. Then only this table is actually appropriate. If they are over reinforced, then this table will not give you the correct calculations, correct values. So, let us see now how this is done. So, in this table, first we calculate something called reinforcement index. Now, what is the reinforcement index is? It is kind of a normalized section parameters. So, this is your reinforcement ratio, which is AP by BD, and we also multiply that with characteristics of strength of steel divided by characteristic strength of concrete, right. And this table 11 gives you two values for both pre-tension and bonded post-tension. Actually, it does not cover unbonded system, right. Okay. And the values of FPU and XU at ultimate condition are given as a function of your value 0.87 FPK. Okay. That means I get this ratio, then FPU will be equal to whatever the value that is given in the table multiplied by 0.87 FPK. Similarly, XU will be the value that I get from the table multiplied by the effective depth will give me the XU and FPU values. So, this is called reinforcement index. So, typically when we do the moment curvature analysis, so you would have, if you plot this, you get this kind of a response, where if I plot MUR and this, let us say if I put reinforcement ratio like this, and somewhere here you get rho balanced. So, you will find that this is basically your rho minimum, and because every cross section we should also put some minimum steel, so that right after cracking the section should not fail. The section should have some post cracking strength. That is the reason minimum steel has to be provided, right. And different codes gives you different ranges for minimum steel, but the objective of providing minimum steel is to ensure that after cracking the section should have some reserve strength, so that it can absorb the energy during cracking. Now, this approximate method, you can see that higher in this region, if you look at it, in this region, so this region, that means from rho minimum to rho balance, you can see that the moment resistance is actually proportional to the amount of reinforcing steel that is provided, and then we know that when the reinforcement steel is less than rho balanced, we are in the under reinforced regime. That means the steel is going to reach yielding, right. So, we have to look all these things and then see how to use in the calculations. Now, for this particular cross section, now let us see from both strain compatibility approach and from approximate method what kind of values that we are getting. So, we are looking at a cross section, simple cross section with a width of 300 mm and with the overall depth of 650 millimeter, and I have an effective cover of 50 mm. So, the effective cover is from the CG of the steel to the bottom, I am having 50 millimeter, right, and characteristic strength is 1860 megapascal, and cylinder compressive strength is 40 megapascals, and we have seen that this corresponds to FCK value of 41.75 megapascal. So, we have seen how to get that value, and the initial strain is given as 0.0065, and we are going to use idealized design bilinear curve for pre-stressing steel. So, code gives you an option. So, we are going to use idealized bilinear curve. So, what are the steps involved? Again, we are doing the calculation at ultimate. So, at ultimate, again epsilon Cu is fixed as 0.0035, but I do not know what is epsilon Pu. So, to calculate epsilon Pu, first I have to assume the value of Xu and then calculate your epsilon P, and then from the design stress strain curve I get Fp. Then after that I have to make sure that Cu is equal to T. So, that means this 0.36 FCK B times Xu should be equal to AP times Fp U, or Fp I should say, Fp I have to get. Then once equilibrium condition is satisfied, then I can calculate your moment resistance and curvature. So, this is the process using strain compatibility approach. Now, let us look at for this particular section. Again, we have taken again condition as 0.0035, and we do not know what is Xu. So, we are going to assume some value, and at ultimate condition we know that this Cu at ultimate concrete force and compression is going to be 0.36 FCKB into Xu, and but we do not know what is Fpu. So, that again is function of your strain in the pre-stressing steel. Strain in the pre-stressing steel, if you see this epsilon P, the total value I can get only from here. Now, from similar triangle quickly we can see what is delta epsilon P here. So, if you see this distance is D, or maybe I should say, actually this is what we are looking at, right. So, we are looking at this location, right. So, let us say this is epsilon Pi, and this is delta epsilon P. So, let us assume that this is epsilon Pi and this is delta epsilon P, right. So, what is delta epsilon P at this location? So, I am calculating this strain gradient. This distance, if you look at it, it is going to be again D is from here, okay, this is D, from here to here is D. So, this is going to be D minus Xu. So, from similar triangle we can see that 0.0035 strain is for a distance of Xu. For D minus Xu distance, it is going to be delta epsilon P. So, I can from this I can get delta epsilon P, then total epsilon P is going to be epsilon Pi plus delta epsilon P, because this can be calculated once I assume Xu. Okay, once Xu is assumed, then I can get all these values, right. So, we can get this here. Okay, so, that is what we are going to do. We are going to assume Xu is equal to 200 millimeter, and then delta epsilon P from strain gradient we can get like this, and we substitute this value for epsilon Cu 0.0035, and D is equal to 600 that we have taken, because overall depth is 650, H is 650, right, and D is 650 minus 50, which is 600 millimeter. So, we have taken that, and Xu we have taken it to be 200. So, if you substitute that, the strain gradient value at the level of pre-stressing steel is 0.007. This is your delta epsilon P. Now, what is the actual strain at ultimate condition? It is 0.007 plus initial strain, which is 0.0065, which is 0.0135, right. So, this is what we are showing here. So, if you go back to the idealized bilinear curve, so we are here 0.0135, and this is, so somewhere here. So, this is your yielding, right, and this is your ultimate epsilon PU, right. So, we are going to be somewhere here, which is somewhere here 0.0135. So, for that you can use this constant equation, you can find out what the values are, right. Yeah. So, we get that means for this strain my stress is 1407.8 plus the difference multiplied by this elastic. This slope is 1405 megapascal. So, you substitute that, you get a stress of 1496.7 megapascal, right. Now, what is the tension force? Tension force is Fp multiplied by the area, which gives me 1646.4 kilonewton. Now, you see Cu is equal to compression force in concrete is 0.36 FCKB into XU, and we know if you substitute FCK calculation works out to be 41.75 megapascal, and Cu is working out to be 900. Now, you see here Tu is greater than Cu. Now, I have to reduce Cu. So, how can I reduce Cu? If you see in this equation, I cannot change FCK, and I cannot reduce B, which is already given to you. Only thing I can reduce is Xu, right. So, in this case Tu is greater than. So, Cu has to be increased, right. So, I can increase Cu only by increasing the neutral axis depth. So, if Cu is going to be increased, then I have to increase the neutral axis depth, right. So, in this case I have to increase Cu. So, I have to increase higher value of Xu. So, we are going to use Xu equal to 349.5 millimeter, right. So, we are going to assume Xu is equal to 349.5 millimeter. Delta epsilon P is working out to be this. Again, for this revised neutral axis depth, we put 600 minus this by this, again similar triangle is this, and epsilon Pu for the revised neutral axis depth is 0.00251 plus 0.0065, which is 0.009. And again using the bilinear stress strain curve, that what we have discussed in the previous slide, for this particular strain of 0.009, I get a stress of 1433.3 megapascal. Now, what is tension force? Again Fpu multiplied by Ap will gives me this, the compression force of this. So, you can see that nearly Cu is equal to Tu. So, the equilibrium condition is satisfied. So, equilibrium is satisfied, right. So, then moment resistance I can get Tp is the tension force in the pre-stressing steel, or maybe I should say here, this also Tu or Tp or whatever, right, and 1577 into this, and then you get 714.7 kilonewton. Now, curvature at failure is epsilon Cu by Xu, then I get 10 into 10 to the power minus 6 per millimeter, right. So, this is using your strain compatibility approach, how to get moment and curvature for one strain value, which is 0.0035. The only thing is we do not know what Xu will lead to equilibrium. So, we are doing it in iterative way. If you have linear elastic and plastic relationship, it is relatively straightforward, but now I have a hardening curve in the steel. So, depending upon where I am there, it is a bilinear response. So, I have to use this kind of depending upon the strain level, I have to calculate the stress using the steel constitutive law that what we have assumed. Okay, the same section now let us calculate using approximate method from table 11 in IS 1343. Okay. So, as we calculated this parameter called reinforcing index, which is WP. APS is 1100 millimeter square, FPU is 1860, B is 300, D is 600, and FCK is 41.7. So, you get 0.272, and if you go back to the table and you find for this reinforcement ratio, FPB is nothing but this value works out to be 1. So, my stress is going to be 0.87 into 1860, which is 1618.2 megapascal. My tension force is 1100 into this, so 1780 kilonewton. And for pre-tensioning, we are also getting Xu by D equal to 0.592. So, Xu works out to be 355.2 millimeter. and compressive force is 0.36 FCK B into XU. So, it works out to be 1602 kilonewton. And you find that you get again, so nearly you see there is you see here Cu is actually not equal to Tu. So, if I use approximate method, you can find that because it is done in a very simplified way. So, if I put all these values, actually we are not getting the equilibrium satisfied. So now because the equilibrium is not satisfied, now I can get moment resistance from either of these values, right. And now in this case, if I take tension force for calculating the moment resistance, which is 1780 times d minus 0.42 XU, I get a moment resistance of 802 kilonewton meter, and curvature is epsilon Cu 0.0035 by this, I get 9.85 into 10 to the power minus 6. So, but you can ask me, why did you take with the tension steel? If you want to be conservative, I can take it with Cu as well. So, in this case, then MER will become, if I take Cu, again it is going to be Cu times d minus 0.42 XU, right. So, then right. So, Cu is now 1602 times 600 minus 0.42 times 355.2. So, if you substitute that, you will get a lower resistance for moment if I take compression force, right. So, this is what we are summarizing in this table. If you use strain compatibility approach, which is a more correct and rational approach, you get neutral axis depth of 349.5 and a tension force of 1577, compression force. So, here both of them are equal and I get moment resistance of 715 and curvature at failure of 10. If I use approximate method, you get slightly a higher neutral axis depth, but the major issue is you find that the Cu in both of them, Cu and Tu, they are not equal, right. So, if I take is calculated based on the tension force. If I am using compression force, this is based on Cu times d minus 0.42 XU, that what we talked about, 722. So, in this case, in approximate methods, you have to choose whichever the least and then use it in your moment calculations, then you get 722. So, then that 722 is pretty close to that of what we get using strain compatible approach. So, but the thing is, the equilibrium condition is not really satisfied if I am using approximate method. So, because it is a very crude way of calculating the moment resistance. So, and I would suggest you go ahead and use strain compatibility, which is very easy to do it if you can develop a simple spreadsheet or a MathCAD or MATLAB program. So, you can quickly do strain compatible approach for any sections, right. So, now what are the limitations of IS 1343 method? If you look at the approximate method, they cannot really take into account the contribution of passive reinforcement. So, the table, it tells you value only based on WP, the reinforcement index, right, reinforcement index based on only based on pre-stressing steel, is not. So, again the method is not really accurate for high reinforcement ratio. If you put lot of pre-stressing steel, then this method is not really applicable. And again, if you have pre-stressing steel on the compression zone, they are also ignored. So, the approximate method in IS 1343 has lot of limitations. I would strongly recommend you to use strain compatibility approach for calculating the moment resistances.